What if everything you see, touch, and feel, every atom in your body, every star in the sky, every moment of your life, is actually a hologram? Not a metaphor, a literal projection from a distant two-dimensional boundary. That sounds like science fiction, but in 1994, Leonard Susskind proved it might be true. He showed that our three-dimensional universe could be nothing more than a shadow cast by information living on a two-dimensional surface. And it all started with a fight about black holes. To understand why this matters, you need to know one thing about Leonard Susskind. He doesn't back down. Born in the South Bronx, son of a plumber, Susskind had clawed his way into theoretical physics through sheer stubborn brilliance. By 1993, he was a professor at Stanford, locked in what would become a 28-year battle with Stephen Hawking over whether information could be destroyed in black holes. Susskind's answer was black hole complementarity, the idea that two observers could have completely different but equally valid descriptions of the same event. An observer falling into a black hole sees information cross the horizon and fall in. An observer outside sees that same information encoded on the horizon's surface. Both descriptions are true. Neither observer can see a contradiction. It was radical. Most physicists thought he'd lost his mind. But then something unexpected happened. Gerard Hooft, a Dutch Nobel laureate, one of the sharpest minds in physics, had been thinking about the same problem independently. Hooft had noticed something strange about black hole entropy. The amount of information a black hole can hold isn't proportional to its volume the way you'd expect. It's proportional to its surface area. The bigger the horizon, the more information it can store. That's weird. It's like saying everything inside a room is actually written on the walls. Susskind and Hooft started talking. Conferences, hallway conversations, emails back and forth across the Atlantic. They were both circling the same impossible idea. What if the black hole horizon wasn't special? What if ALL of space worked this way? The stakes couldn't have been higher. If they were right, the fundamental nature of reality, the very structure of space itself, was nothing like what anyone had imagined. Three-dimensional space might be an illusion. Everything we experience is depth, volume, and solid matter could be a projection from a lower dimensional surface. This wasn't just abstract philosophy. This was physics with testable consequences. And if it was true, it would change everything we thought we knew about the universe. By late 1993, Susskind was alone in his Stanford office, staring at equations about black hole entropy and information bounds. The pieces were starting to fall into place. What he was about to propose would be the most cited paper of his career, a principle so profound that physicists are still working out its implications 3 decades later. Here's the problem: Susskind was wrestling with information. In physics, information is sacred. Quantum mechanics says that information can never be destroyed. You can scramble it, hide it, spread it across the universe, but it has to exist somewhere. It's one of the most fundamental rules in all of physics. Break it, and you break quantum mechanics itself. But black holes seem to violate this rule. Stephen Hawking had shown in 1974 that black holes radiate energy. They glow with thermal radiation and slowly evaporate. The problem: that radiation looks completely random. It carries no information about what fell in. A black hole formed from a collapsing star should radiate differently than one formed from pure energy or a giant encyclopedia. But Hawking's calculations showed they'd look identical. The information about what went in seemed to be gone forever. This was the information paradox, and it threatened to tear a hole in the foundation of physics. Susskind had proposed complementarity as a solution. The information isn't destroyed, it's just described differently by different observers. But that raised another question: if the information is preserved, where exactly is it stored? Think about it this way. Imagine you have a giant library, millions of books, vast rooms, endless shelves. Intuitively, you'd assume the amount of information in that library is related to its volume. More space, more books, more information. That's how we think space works, but black holes don't follow that rule. Jacob Bekenstein had proven in 1973 that a black hole's entropy, which measures how much information it can hold, is proportional to its surface area, not its volume. Double the radius and you quadruple the surface area. The black hole can now hold 4 times as much information, but you've increased the volume by a factor of 8. Something doesn't add up, it gets weirder. There's an absolute limit to how much information can fit in any region of space. That limit is given by the Bekenstein bound. Roughly 1 bit of information per Planck area. The Planck length is 1035 meters, incomprehensibly tiny. The Planck area is that squared, and according to Bekenstein, you can't pack information any denser than 1 bit per Planck area on the surface of a region. Not the volume, the surface. Susskind kept coming back to this. If you want to know the maximum information content of any region, a room, a planet, a galaxy, the entire observable universe, you don't calculate its volume. You calculate its surface area and divide by the Planck area. That number tells you the maximum number of bits that region can possibly contain. But why? Why should the information content of a 3-dimensional region be limited by its 2-dimensional boundary? It would be like saying you can't put more files on your computer's hard drive than you can write on the outside of the computer case. That makes no sense unless the hard drive isn't actually storing the data, unless the data is fundamentally encoded on the surface, and the 3-dimensional interior is just a projection, a convenient way for us to visualize information that's really living somewhere else. Gerard Hooft had been thinking along similar lines in Utrecht. He'd published a paper in 1993 arguing that the physics on the horizon of a black hole contains all the information about the interior. The horizon is like a hologram, a 2-dimensional surface encoding 3-dimensional information. But Hooft's idea was still limited to black holes. Susskind started to wonder, what if it's not just black holes? What if it's everything? Here's the thought experiment that crystallized it for him. Imagine you have a region of space, any region. Doesn't matter what's inside it. Now imagine compressing that region, squeezing it smaller and smaller. At some point, if you compress it enough, it will form a black hole. The moment it does, the Bekenstein bound kicks in. The information content of that region is now limited by the area of the black hole's event horizon. But wait, the information was already in that region before you compressed it, which means the information content was always limited by what would eventually become the horizon's surface area. The 3-dimensional interior never actually mattered. The information was always constrained by the 2-dimensional boundary. Susskind realized something profound. 3-dimensional space might be like a hologram. You know those holographic images where a 3-dimensional scene appears to float in space, but it's really encoded on a flat 2-dimensional plate. Shine a laser through the plate and the 3D image appears. But all the information, every detail of depth, color, and shape is stored on that 2D surface. What if the universe works the same way? What if all the information about our 3-dimensional world is actually encoded on a distant 2-dimensional boundary, and everything we experience as space, depth, and volume is just a projection? In 1994, Susskind published The World as a Hologram. The paper was built on a simple but devastating argument. Take any region of space, any region at all, a box, a sphere, the interior of a galaxy. There's a maximum amount of information that region can contain, and that maximum is determined by its surface area, not its volume. 1 degree of freedom per Planck area on the boundary. Here's what that means in practice. Imagine you want to describe everything inside a sphere, every particle, every field, every quantum state. Classical intuition says you need a number of variables proportional to the volume. More space, more stuff, more variables needed to describe it. But the holographic principle says no. You only need a number of variables proportional to the surface area. The boundary contains all the information you need to fully reconstruct the interior. It's as if the three-dimensional interior is redundant. It's a derived concept, not a fundamental one. The real physics, the actual information, lives on the two-dimensional surface. The three-dimensional space we experience is like a shadow cast by that surface. Susskind worked out the consequences. In the paper, he showed that this principle isn't just about black holes. It's universal. It applies to any region of space, anywhere in the universe. The holographic principle is a statement about the fundamental structure of reality. And here's where it gets truly bizarre. Particles have to change their properties at high energies to make this work. Think about a particle with momentum. The higher the momentum, the smaller its wavelength. That's basic quantum mechanics. But Susskind showed that if the holographic principle is true, something weird happens when particles reach extremely high energies, close to the Planck scale. Instead of getting smaller, they start getting bigger. Their effective size grows with their momentum. This is completely unlike anything in ordinary physics, but it's necessary to keep the information bound satisfied. If particles kept shrinking at arbitrarily high energies, you could pack more and more information into a finite region just by boosting particles to higher and higher speeds. That would violate the Bekenstein bound, so nature prevents it. Particles grow. This was later confirmed in string theory. Strings, the fundamental objects in string theory, have exactly this property. At low energies they look like point particles, but at high energies they spread out, the string grows. Susskind had predicted a fundamental feature of string theory directly from the holographic principle. But the most profound implication was this: if the holographic principle is true, then space itself might be emergent, not fundamental, not built into the bedrock of reality. Space, the three-dimensional arena we think of as the stage where physics happens, might be a derived concept, an illusion created by information living on a lower dimensional surface. Susskind laid all of this out with crystalline logic. The paper is only about 15 pages long, but every sentence is packed with implications. He connected black hole thermodynamics to information theory to quantum gravity to string theory, weaving them into a single coherent picture. The core argument goes like this: one black hole entropy is proportional to horizon area. A Bekenstein-Hawking result established 2 entropy measures information content, a standard statistical mechanics. 3, therefore, the maximum information in any region is proportional to its boundary area, not its volume. The key leap. 4, if the maximum information is determined by the boundary, then the boundary description might be complete, a holography. 5, the three-dimensional interior could be a holographic projection from the two-dimensional boundary. A revolutionary conclusion. Now, here's the beautiful part. This wasn't just speculation. Susskind made concrete predictions. He calculated what had to be true for the principle to work. Particles must grow at high energies. Information must be preserved in black hole evaporation. There are limits to how much you can localize information in a finite region. These are all testable consequences in principle, if not yet in practice. And crucially, Susskind wasn't alone in this discovery. Gerard Hooft had independently arrived at nearly the same idea around the same time. They were both building on Bekenstein and Hawking's work on black hole thermodynamics, both thinking deeply about the information paradox, and both reached the same radical conclusion from different angles. In physics, when two people independently discover the same deep principle, it's usually a sign that the idea is real. It's not a quirk of one person's mathematical approach or a personal bias. It's something fundamental trying to reveal itself through the equations. Susskind acknowledged in Hooft's parallel work in his paper. They'd been in conversation, comparing notes, building on each other's insights. This wasn't a race, it was a collaboration at a distance. Two physicists separated by the Atlantic Ocean, both seeing the same hidden structure in the laws of physics. The paper ends with a profound observation. Susskind writes that the holographic principle suggests a deep connection between quantum mechanics and gravity that we don't fully understand yet. The fact that information bounds are set by geometry, by areas, not volumes, hints at something fundamental about how space-time and quantum information are woven together. At the time, nobody knew exactly what that connection was, but the holographic principle would become one of the guiding ideas in theoretical physics for the next 3 decades. It would lead to the ADS-CFT correspondence, Joan Maldaceno's breakthrough showing that a theory of quantum gravity in a certain curved spacetime is exactly equivalent to a quantum field theory on its boundary. It would reshape how physicists think about quantum gravity, cosmology, and the nature of space itself, all from this one paper. The World is a Hologram, published in the Journal of Mathematical Physics in 1995, based on the 1994 preprint. Today it has over 400 or 500 citations. It's Susskind's most cited work, and it started with a simple question: if information can't be destroyed, where is it stored? When Susskind presented the holographic principle at conferences in 1994 and 95, the physics community didn't know what to make of it. Half the room thought it was brilliant. The other half thought he'd gone off the deep end. The idea that 3-dimensional space might be an illusion, a projection from a 2-dimensional surface, sounded more like philosophy than physics. String theorists were intrigued but cautious. Quantum field theorists were skeptical, and general relativists, many of them hated it. The idea that space-time geometry might be emergent, not fundamental, struck at the heart of Einstein's vision. Susskind recalls that when he gave talks on this, Ed Witten, widely considered the smartest physicist alive, would sit in the front row with an inscrutable expression. Not dismissive, but not convinced either, just thinking, trying to work out whether this crazy idea could actually be right. The problem was that the holographic principle was more of a guiding principle than a concrete theory. Susskind had shown that the information in any region is bounded by its surface area, and he'd argued that this suggests a holographic relationship between bulk physics and boundary physics, but he hadn't constructed an explicit example. He couldn't point to a specific theory and say, look, here's holography in action. That would take another 3 years. In 1997, Joan Maldaceno, a young physicist at Harvard, published one of the most important papers in theoretical physics history. He showed that a particular quantum theory of gravity in ante de Sitter, ADS space, is exactly equivalent to a conformal field theory, CFT, living on the boundary of that space. ADS-CFT correspondence, a precise, concrete realization of the holographic principle. Maldaceno's discovery changed everything. Suddenly, holography wasn't just a beautiful idea, it was a mathematical fact. You could take a 5-dimensional gravitational theory, calculate something, and get the exact same answer as a 4-dimensional quantum field theory on the boundary. The bulk and the boundary were 2 descriptions of the same physics. The field exploded. By the early 2000s, thousands of physicists were working on ADS-CFT and its implications. It became the dominant framework for thinking about quantum gravity. And at the heart of it all was Susskind's holographic principle. At Hooft and Susskind's work was vindicated. The holographic relationship they'd intuited from black hole thermodynamics turned out to be a fundamental feature of quantum gravity. Spacetime really could emerge from quantum information on a boundary. 3-dimensional space really could be holographic. But here's the thing, the story doesn't end there. ATTIS CFT is beautiful, but it describes a universe with negative curvature, anti-Sitter space. Our universe isn't like that. We live in a universe with a positive cosmological constant accelerating expansion to Sitter space. And holography into Sitter space is vastly more difficult. Susskind knows this better than anyone. In 2021, he co-authored a paper proving a no-go theorem for de Sitter holography. The go here, Susskind's GKAS theorem shows that you can't have perfect de Sitter symmetry A and finite entropy at the same time. Something has to give, so the question that launched the holographic revolution in 1994 is still being answered today. We know holography works in ADS space. We think it works in some form for black holes. But the holographic description of our actual universe, the one we live in with its accelerating expansion and cosmological horizons, remains one of the deepest open problems in theoretical physics. And Susskind, now in his 80s, is still working on it. Still publishing papers, still pushing the boundaries, still trying to understand what holography means for the real cosmos. The reaction to the holographic principle has evolved over 3 decades, from skepticism to acceptance to active research. It's now a cornerstone of modern theoretical physics. When young physicists learn quantum gravity, they learn about holography in the first few lectures. It's foundational, but the revolution isn't over. The holographic principle pointed the way, but we're still following the path. We still don't fully understand how spacetime emerges from quantum information. We don't know the holographic description of cosmology. We don't know if our universe really is a projection from a distant boundary, or what that boundary even is. Those are the questions that keep Susskind up at night. And they're the questions that will define theoretical physics for the next generation. So what does it actually mean if the holographic principle is true? First, space might not be fundamental. Everything we think of as three-dimensional, depth, volume, the solid matter around us, could be an emergent phenomenon. The real physics, the actual information, might live on a two-dimensional surface far away, and the 3D world we experience is just a convenient description, a holographic projection that helps us make sense of the underlying data. Think about that for a second. Your body, this room, the Earth, the solar system, all of it might be shadows cast by information encoded on a distant boundary. Not shadows in the usual sense, obviously. But mathematically, holographically, the three-dimensional description might be secondary to a two-dimensional one. Second, this connects quantum mechanics and gravity in a way we didn't expect. The fact that information bounds are set by areas, by geometry, tells us that space-time and quantum information are deeply intertwined. Gravity isn't just a force acting in space-time, it emerges from the way information is organized. Space-time geometry is, in some sense, a manifestation of quantum entanglement. This is what Susskind's later work with Joan Maldacena on EPR was all about. Wormholes, geometric connections in space-time, turn out to be quantum entanglement in disguise, geometry as entanglement. That's holography in action. Third, there are limits to information density that we're still working out the implications of. You can't pack arbitrary amounts of information into a finite region. There's a maximum set by the Bekenstein bound. This has consequences for quantum computing, black hole physics, and the ultimate fate of information in the universe. And fourth, this changes how we think about cosmology. Our universe has a cosmological horizon, a boundary beyond which we can't see because the universe is expanding too fast. If holography applies to our universe, then everything inside our cosmological horizon, everything we can ever observe or interact with, might be encoded on that horizon. The entire observable universe could be a holographic projection from a sphere at the edge of space. Current research is pushing these ideas further. Physicists are using holography to study quantum gravity, to understand black holes, to explore the early universe, and to connect string theory to observable physics. The ADS-CFT correspondence has become a tool for understanding strongly coupled quantum systems, systems where particles interact so strongly that normal methods break down. Condensed matter physicists are using it to study exotic states of matter. Nuclear physicists are using it to model the quark-gluon plasma. The holographic principle has spread far beyond where Susskind first proposed it. It's become a central organizing idea in 21st century physics. But the biggest question remains, is our universe actually holographic? We don't know for sure. We have strong evidence that it works for 8S space. We have good reasons to think it applies to black holes. But our universe is de Sitter, and de Sitter holography is still an open problem. Susskind is working on it, so are dozens of other groups around the world. They're making progress slowly, piecing together what holography means when the cosmological horizon depends on the observer. The answer might reshape physics as profoundly as quantum mechanics and relativity did in the 20th century. Because if holography is right, if space really is emergent, if the universe really is a projection from its boundary, then we've been thinking about reality wrong for a very long time. And that's the beauty of physics. Every answer reveals deeper questions, every discovery opens new frontiers. And G 2500, 2700, 300 words 30 years ago, Leonard Susskind published a paper arguing that the universe might be a hologram. At the time, it sounded crazy. Today, it's one of the foundational ideas in theoretical physics. Here's what strikes me about this story. Susskind wasn't trying to be provocative. He wasn't making wild speculations for attention. He was following the logic of black hole thermodynamics to its inevitable conclusion. The math said that information is bounded by surface area, not volume. So he asked, what does that mean? And when he worked it through, he found himself staring at something impossible. Three-dimensional space might be an illusion. Most physicists would have backed away from that conclusion. It's too strange, too radical, too hard to accept. But Susskind has never backed away from an idea just because it makes people uncomfortable. If the equations say it, you take it seriously. That's been his approach for 50 years, and he's still at it. In his 80s now, still publishing papers, still teaching at Stanford, still pushing boundaries. His most recent work on de Sitter holography is some of the most technically challenging physics out there. He's trying to solve a problem that might not have a solution in his lifetime. But that's what makes it worth doing. The holographic principle points toward something profound about the nature of reality, something we're only beginning to understand. It suggests that spacetime is emergent, that geometry is quantum information in disguise, that the universe has a structure we never imagined. And if Leonard Susskind is right, and increasingly the evidence says he is, then reality is far stranger, far more beautiful, and far more deeply interconnected than we ever dreamed. That's the universe Susskind has spent his life uncovering. And the story is far from over.